Hello, hello. Okay. Hi everyone, we'll be starting class in 1 to 2 minutes time. Alright, hi everyone. So today's schedule for what we're doing is that we're going to be focusing on finishing up the Fourier Transform lectures. So that'll be the Fourier Transform 2 and 3 lectures in particular for today. After which we'll move on to selected questions from forum set 3, which you guys voted on. I'll do the top 3 questions from those, and afterwards I'll post up the general solutions for all the problems in problem set 3 on my learning. And if time permits, we'll do a couple of questions that are somewhat related to the type of questions you may expect on your midterm in particular, because of the request that we got yesterday from some students asking about a midterm review session in particular. But like I said, we're starting with the Fourier Transform lectures because we're trying to finish up this content for today. So the second Fourier Transform lecture here, which we're going to be starting on, is going to focus on a little more on the usage of the Fourier Transform. And the third Fourier Transform lecture will focus a little more on the Fourier Transform tables and how it can be used for different aspects and so forth. Alright, so let's get to it. So the purpose of the Fourier Transform, like I've said before, is basically you transform your time domain signal here, being a continuous time domain signal, into a continuous frequency domain signal. So basically, in transforming your time domain signal here into a frequency domain, we basically obtain the spectrum of the signal as of such. And the Fourier transform is basically used for non-periodic signals, whereas we observed that the Fourier series was used for periodic signals in particular. Now, when you obtain the spectrum of the signal, being the representation of the signal itself, the bandwidth of the signal would be the maximum width that the signal occupies on the baseline here with respect to omega. So, as we can see here on the baseline here, the signal goes from minus omega s to positive omega s, and if we take the magnitude of that, that's going to be 2 omega s. So we basically say that this signal in particular, when it transforms into the Fourier representation, it has a bandwidth of 2 omega s accordingly by measuring the base of width of the signal here. Now, in yesterday's lecture, we saw that it was possible for us to apply frequency translation by using the exponent form here in the time domain. And what this basically meant was, if we watch this omega naught here in the exponent power, this would actually determine if the signal was shifted to the left or right accordingly. But if it was positive omega naught here, this would be omega minus omega naught. If it was minus omega naught here, it would be omega plus omega naught here for the shift. So if we had, in this case, positive omega naught in the time domain, in the frequency domain it's going to be omega minus omega naught. And we basically, if we had our original Fourier representation of x of t being x of j omega here, what this means is that because we have minus omega naught in the frequency domain, that means we shift the signal in the frequency domain to the right by a factor of omega naught. So instead of the signal all being centered about 0, because we have the shift factor here of omega naught, the signal is now centered about omega naught in particular. And because we knew that the ends of the signal, in this case the bandwidth, was omega s and minus omega s, that means the uppermost limit here is going to be omega naught plus omega s, and the lowermost limit here is going to be omega naught minus omega s in particular. And the reason for doing this frequency translation, it gives us to a principle that we refer to as modulation. And a practical application of this is like, let's say you want to do data transmission, in particular, wireless data transmission. So perhaps your input signal is somewhere in the realms of kilohertz. So let's say probably your voice. And after your voice is transduced from an analog signal to a digital signal via the microphone and so forth, before it can actually be transmitted onto the wireless carrier range, so let's say if it's a cell phone signal, I was using GSM, that means that instead of the signal being in kilohertz, it now needs to be represented at megahertz, because GSM transmits at around like 800 to 900 megahertz. So in doing so, after the signal is amplified and so forth, it actually is modulated, which basically is a simple form of frequency translation to move the signal contents from the kilohertz range into the megahertz range, which is required for the data transmission for GSM, which is going to be somewhere around 800 to 900 megahertz accordingly. So the reason why frequency translation actually is quite important is because it helps us to transmit data at faster frequencies, or to de-transmit data, for lack of a better word, to get back the original contents of the signal. And as of such, when you go into your communication systems course next semester, you'll be learning a little bit more about modulation. In particular, you'll learn about amplitude modulation and frequency modulation, but we don't really discuss that in this course. We just basically discuss the brief physical property of frequency translation here in particular. So, because we're going to be focusing on the use of the Fourier transform, and we saw basically for the Fourier transform respect to unit impulse and then the rectangular pulse in yesterday's lecture. We're going to be focusing on a little more of a practical signal here, and in this case we're going to be looking at the Fourier transform of the unit step. So in this case, we need to make sure that we define the unit step accordingly, because we know for anything before t equals 0 it's going to be 0, and then t more than equal to 0 it's going to be 1. And then we're actually going to apply the Fourier transform integral equation in order to transform the signal from x of t into x of j omega. But what we're going to observe is that in doing this transform, we're going to have to do a little bit of a different approach in particular. So when you actually apply this accordingly into the integral form here, and you try to integrate e to the minus j omega t with respect to positive omega and minus omega, and if you try to limit evaluate and so forth, you see that it gets into some really complicated mathematics. Try to do this limit evaluation, it will go like all haywire all over the place, because you have a cosine and sine term here which basically don't have finite maxima and minima. So you won't get like any finite values once t keeps on changing here accordingly. So as of such, in evaluating this Fourier transform, you want to require another approach in particular. And this approach is typically taken for like all general other purpose signals. So it's a little bit important as to how you actually do the Fourier transform accordingly when using this approach. So you can actually use the Laplace transform to do half of the work required in solving for the Fourier transform. So the Laplace transform basically knows that we know from the unit step it will be basically 1 on s. And if we basically said what s was equal to j omega accordingly to map the Laplace to the Fourier, that basically means that we can just say u of j omega here will just be 1 on j omega. But this is only partially correct, because remember the Laplace transform integral limits only goes from the 0 negative to positive infinity limits, whereas the Fourier transform limits goes from negative infinity to positive infinity. So we have only accommodated for 0 negative here to positive infinity. We haven't accommodated for negative infinity to 0 as such. So we need to account for that other half of the integral limits for the Fourier transform in particular. So in order to accommodate for this, that means we need to figure out, well, okay, in the time domain, this signal needs to have an average or DC value. So how do we actually calculate this average or DC value in particular? And this actually goes back to the evaluation that we did for the Fourier series, where we had our A0 component, because if you recall, that A0 component basically helped us calculate the average or DC value for the entire signal. So in applying this A0 formula from the Fourier series here, you'll see that we have L, but we also know that because the signal is aperiodic in nature, that means t is approaching infinity. So in order to do this evaluation, we don't substitute any numerical values here for L as of such, because no, L is basically half of the periodic sign. So we leave L here, and when we actually do the evaluations in the integrals, you'll see basically that the L components, when we substitute them in, they will cancel out with each other, and we'll end up getting a numerical value in the end as of such. So when we actually do this integral evaluation here for the unit step, we basically see that for anything less than 0, the unit step was 0, and then for anything greater than 0, the unit step basically was 1. So it comes like we're just evaluating the integral part here in particular. And because this here, when it resolves, is go to x, and then we have to substitute in limits L and 0. But because when we substitute in 0, this entire thing here will just go to 0 only. That means we'll end up with L divided by 2 L's, and the L's here will just cancel out, so we end up with a value of a half. So when you actually apply this accordingly for the evaluation of the average or DC value, just remember that the L values will just cancel out each other, so you can use the L components as they are evaluating this in the A0 formula here. Now remember, when we got that half, that was with respect to the time domain, and as of such, that average or DC value adds on to the evaluation from using the Laplace transform accordingly, because the Laplace transform only gave us the first half of the Fourier transform, and the average or DC value gives us the second half of the Fourier transform as such. But that was in the time domain. So because we have this in the time domain, we actually need to Fourier transform this constant value here to get its representation in the frequency domain, and that will give us the entire representation of u j omega here. So because we have this constant here for the Fourier transform DC value that we need to evaluate, we need to record the relationship of the impulse, sorry, the unit impulse here, with respect to the j omega domain. So when we translate delta t here, this actually maps to 1 in the j omega domain. And in some cases, it actually can also map to 1 on 2 pi because of that 2 pi component when we actually apply it to the Fourier transform. So because when you actually apply the integral limits here for delta of omega, because this is going to be with respect to our evaluation here, to get this to d omega as of such for x of t, we basically see that when we actually apply the equation here accordingly, and we conduct the integral evaluation for x of t here as of such, we see that because it's delta omega e j omega t and the integral here is done, this goes back to the mathematical properties of the unit impulse, and basically the area under the unit impulse will just be 1. So this entire integral form here will just resolve to a value of 1, and we have this 1 on 2 pi constant on the outside here, so this basically gives us 1 on 2 pi as of such. So as of such, because the inverse Fourier transform and the Fourier transform can be mapped accordingly by using the 1 on 2 pi constant as such, because what we saw in yesterday's lecture, if we have 1 on 2 pi in the time domain, this could just basically map to delta omega in the frequency domain as of such. And similarly, if we have 1 on 2 pi in the omega domain, this just maps to 1 in the time domain accordingly, because of the nature of the Fourier and inverse Fourier transforms. So basically, because we know that when we just now evaluated the x of t signal for delta omega, such that in our previous slide here, when we did the inverse Fourier transform, we got x of t basically be equal to 1 on 2 pi for delta omega. We can map this accordingly to our equation here, and then we can manipulate it such that we get only a value of a half here on the time domain side, and we get its frequency representation on the omega side here as of such. So basically a half, which is the time domain value, will map to pi delta omega in the frequency domain, which is actually what we require for our Fourier transform of a half. And as such, when we plug that into our final equation here for the unit step in the j omega domain, it will equal to 1 on j omega, which basically was our Laplace domain evaluation, plus the Fourier transform of a half, and that evaluation here gave us pi delta omega as of. So in doing the evaluation here for the unit step and any other general signal that you may encounter, you can actually use the Laplace transform to shortcut half of your work for respective values in the Fourier transform. Also remember, in doing so, that only evaluates from 0 negative to positive infinity, whereas the Fourier transform goes from negative infinity to positive infinity. That means you're also going to have to factor in the average or DC value as of such for the entire wave, and you can actually evaluate that in the time domain using the A0 formula from the Fourier series. Just remember that the L components, you'll keep that L component in the evaluation for A0, and the L components will basically cancel off each other, leaving you with a numerical value. And then once you have that numerical value, you're free to transform it accordingly using your Fourier transform tables if you can't remember it, or using the information provided here on the slides that actually show you how to map accordingly to get your DC values as of such. In this particular case, you saw that this will basically give us a half mapping to pi delta omega, but this also means that we can multiply both sides by 2 and we can get a value of 1. And we can multiply both sides accordingly by any of values to get the numerical representation here for, let's say, like 3. It could go to the representation in the frequency domain by just multiplying out accordingly to get whatever value is required for mapping your time domain DC signal to your frequency domain representation. Now, the spectrum of this, okay, no, before I go on, are there any particular questions with regards to the Fourier transform of the unit step? Alright, doesn't seem like we have any questions, so I'll be moving on with the lecture itself. So we have our Fourier transform of the unit step here as given by uj omega, and we actually need to observe what does this look like with respect to omega, so basically the spectrum of the signal. And in doing so, when we actually plot this with respect to omega, we basically get this signal here giving us asymptotes accordingly for the thing, for that 1 on j omega value in particular. And then we have our DC value here basically giving us pi delta omega as of such, which contributes also to our asymptote values in particular. The pi delta omega basically represents the Fourier transform of a DC value of a half in the time domain. So basically, when we did the mathematical evaluation of the inverse Fourier transform here for an impulse in the frequency domain, we basically saw that for any impulse in the frequency domain being delta omega, when we actually did all the mathematics behind it, we all got this being equal to 1 on 2 pi, which would be its representation in the time domain, x of t. So 1 on 2 pi in the time domain basically maps to delta omega in the frequency domain. And as of such, because this is a direct mapping, meaning 1 on 2 pi in time is delta omega in frequency, we can manipulate both sides of the equation accordingly by multiplying or dividing components as of such. So this comes like if we just take this pi component here in the time domain and we transfer it directly across into the frequency domain. And this can be done because of the relationship between the Fourier and inverse Fourier transforms. So as of such, because we had 1 on 2 pi here mapping to delta omega, that means if we just wanted the value of a half, we just transfer this pi component across into the frequency domain. So we just get a value of a half here being mapped to pi delta omega as of such. And the reason for why we did this is because remember when we evaluated the Laplace evaluation of the unit step, we only got 1 on s, and we basically said s equals to j omega to shortcut our work, so we got 1 on j omega. But the limit evaluation in the Laplace domain goes from 0 negative to positive infinity, whereas in the Fourier transform, it goes from negative infinity to positive infinity. So as of such, you need to factor in that DC value for the second half of the Fourier transform, and then you can actually apply the Fourier transform, that DC value, which we just did here, to actually get its frequency domain representation, which was pi delta omega. Right. So basically, if we plot that uj omega here, we took the magnitude of it and we plotted the spectrum, we basically see we get some asymptote values here as of such. And the pi delta omega value would just basically be a straight impulse here as of such for the omega value. Right. So for your homework, I want you guys to actually attempt doing the Fourier transform of your standard cosine signal and see if you can actually come up with a representation of it with respect to your frequency translation, and it should be cosine omega minus omega naught and cosine omega plus omega naught as of such. And doing the evaluation, use the exponent form, and remember that it's also possible for you guys to do this using the Euler representation for cosine and sine as well. So that actually should help you guys with approaching this problem in particular. Alright, yeah, that's the end of the second Fourier transform lecture. Are there any further questions at this point? It doesn't seem like we have any further questions at this point, so I'll be moving on to the last Fourier Transform lecture for today. Right. So this last Fourier Transform lecture is going to be pretty short because it basically just details the use of the Fourier Transform table and just some further details before we move on to the content for the next lecture, which will be in 2 weeks' time, which will be the start of word plots in particular. And that's also quite an important topic because that typically is a 10-mark question on your final exam. But for now, we're just going to be discussing the Fourier Transform. When we actually reach that point in time to discuss the word plot stuff, we'll go through that in extreme detail. Actually, how to actually draw up the word plots and evaluate them as of such. So typically when you're dealing with the Fourier Transform in any situation, you'll be given a table of Fourier Transforms, which basically give us your mappings as of such for quick reference. So in case if you guys ever forget what's the mapping for the DC, just remember we have 1 and 2 pi here mapping to delta omega, and this comes like if the two of them just straight equal to each other. And then you could just mathematically manipulate the left hand side and manipulate the right hand side equally to get your values on the left hand side here with respect to DC values, and you'll get the frequency domain representations here with respect to omega accordingly. You'll also be given quick references to like your unit step being u of t, your p of t signal being your rectangular pulse, and then you'll have like standard signals being like e to the minus at u of t, and then t e to the minus at u of t as of such, and then your cosine signals and your sine signals and other stuff as well. But basically you're going to see that the table is very similar to the Laplace transform table. So it just basically represents how you use it accordingly, and if you're solving differential equations in particular, it means that you'll also have to do partial fractions, and then from the partial fractions you get the equivalent transforms from the table, and then inverse Fourier transform them using the table representations to get your answers as of such. But when we actually reach those sort of problems in particular, you'll get enough practice to actually observe what to look for on the transform tables, as well as how to manipulate the differential equations in particular to obtain your solutions. So the main purpose of using that Fourier transform table is actually solving differential equations. And because there will be some situations where your differential equations may have non-causal inputs for future courses, you'll be actually using the Fourier transform in particular to solve these problems instead of the Laplace transform. So we're going to be looking at one particular differential equation here, which we have dy dt plus y of t is equal to x of t. We're given an x of t signal here being e to the minus 2t u of t. So the first order differential for dy dt in your Fourier transform domain would be j omega and y j omega, which basically is similar to s y of s, and we just substitute s equal to j omega. Remember, there's no initial conditions for the Fourier transform because of the integral limits going from minus infinity to positive infinity. So, knowing that this is the first order differential form here mapped to our Fourier transform domain here, basically the differential equation that we had just had before maps to j omega y j omega plus y j omega is equal to x j omega, and then we can factorize out the y j omega here on the left hand side, and we can transfer this value here in brackets here onto the right hand side of the equation and transfer this x of j omega here to have y on x, giving us a transfer function as of such. We also know that if we just want to keep this equation with respect to y j omega, because we have x j omega here on the left hand side, we also had x of t here being e to the minus 2t u of t. And if we look on our transform table, we basically see here that there's an associated transform with the exponent u of t here. So we can actually just watch our transform table and then plug in our A coefficients here to get our representation of xj omega here as of such. Once we substitute that in accordingly, and we rearrange the equation to make y of j omega the subject of the formula, we basically see that's going to be a multiplication of these two factors here with respect to j omega on the denominator. We can then partial fraction this accordingly by using j omega here as our constant, and we can solve for a and b as of such with respect to your partial fraction. So a will be positive 1, b will be negative 1. If you have any trouble doing this, there is a Fourier partial fraction calculator that you actually can use online on Symbolab, if I believe, which actually show you guys all the working as of such. So you actually utilize that to see how to do the partial fraction breakdown for this. But the simplest way is just to say let some value here equal to j omega, and then substitute the values in accordingly to solve for a and b as of such. Because you're just trying to solve for these numerical components here on the numerator. So once you obtain those components and you have your partial fraction representations, you can actually check the tables for the inverse Fourier transforms as of such to get back the representations, and you can actually obtain your answer in the time domain in particular. And what you guys are going to realize here is that this actually is quite similar to actually solving this equation using the Laplace transform, but in such a case that where you have no initial conditions. So like your x0 naught and your y0 naught conditions are basically non-existent, so you just keep treating that as 0, and you're just solving accordingly for that Laplace transform as of such. So if you actually attempt to solve that differential equation here using the Laplace transform, you're supposed to end up with the same answer for y of t here. So now that you can actually observe that for your first order differential equation, try actually attempting this for your second order differential equation here as of such. And remember, it's basically similar to the Laplace transform for getting your d2y dt squared and your dy dt. You just substitute s equals j omega, and you ignore the initial conditions because the Fourier transform does not have any initial conditions to be. So you can do that for all your y components here on your left hand side of the equation and all your x components here on the right hand side of the equation. The frequency transfer function h of j omega here, remember this is going to be y of j omega divided by x of j omega. I'm writing that down for you guys. So h of j omega is basically going to be y of j omega divided by x of j omega. So once you obtain this representation here, right, nice. So once you obtain your representation for h of j omega here being y on x, you can then do your partial fraction accordingly and solve for h of t as of such. And this actually is a good practice problem to attempt because these sorts of problems tend to come on your final exam in particular for the Fourier transform. Or you may also get like example problems doing like evaluate the Fourier transform of the unit step, or for any standard signal using the integral form, and the same steps that we took in the previous lecture will actually help you solve for those in particular. So those are like this particular types of problems that you may encounter with respect to the Fourier transform. You either get a differential equation to solve, or you'll be actually given a standard signal and be asked to evaluate the Fourier transform in it using the mathematical integral operations. So far, with respect to frequency response, you guys actually have only observed two responses, which would be the impulse response and the step response. And the impulse response basically gave us the transfer function for our system, whereas the step response basically gave us the transient response or the damping factors for the system in particular. The Fourier transform, its application basically gives us the response of a system, being the frequency response of the system, to a sinusoidal output. So this basically gives us the response with respect to omega here, where omega can take any frequency in particular. So it comes like if we have our g of t system here, and we subject it to our standard sine wave being sine omega t. We need to figure out, okay, what's going to be y of t here after we do this subjection. of x of t to g of t. Now, if we convert this into our j omega domain, because we have g of j omega here mapping to g of t, that means we have an associated magnitude being modulus of g j omega, and associated phase being the angle of g j omega as such. The shortcut way to write this is modulus of g j omega, and you put your angle side here, and you put phi to indicate the phase difference. So what happens here is that if we watch this accordingly for evaluating the steady state value of y being y ss of t, basically it means that we take the magnitude of g j omega and we factor in our phase here for sine omega t as of such. Your phase here will be mapping to the angle of g j omega in particular. And what you need to realize is that any sinusoidal input that goes into any general LTI system, you're not going to produce any new frequencies. So whatever frequency you inject in there from that sinusoidal input, that's the only frequency you're going to be observing in particular. There will be no generated new frequencies, so there will be no harmonics as of such when doing the frequency response on the system. Basically, the input signal basically will be defined by the amplitude and phase shift of the system, where the amplitude here will be modulus of g of j omega, and the phase shift is going to be phi equal to the argument or angle of g j omega in particular. And g j omega basically will give us the system's Fourier or frequency transfer function in particular, which will give us the mapping between y of j omega to x of j omega, or in time domain terms, the mapping of y of t to x of t with respect to the g of t or g or j omega system. And we'll be observing this in particular with respect to the board plots lecture, which we're going to be doing in 2 weeks' time, as to why this amplitude here for being modulus g or j omega and the phase shift being phi or argument of g j omega here, why these two particular properties are important when we actually hit to the board plots lectures in particular. Alright, so that brings us to the end of the third Fourier Transform lecture and the last Fourier Transform lecture. Are there any particular questions? Alright, doesn't seem like I have any questions with respect to this, so that basically is the end of our Fourier Transform lectures. And at this point in time, we'll be moving on to the selected problem from problem set 3. That's good. Off for the timing. Back into that's okay. Alright, so before I move on, we get results of the poll. Alright, so the results of the poll here basically show us that the majority of people want questions 3, 4, and 5 to be done with this problem set. Whereas question 1 and 2 didn't really have much response. So I guess in 3, 4, and 5 gave you guys the most trouble, or you guys need a little more rectification on actually how to solve these problems. So we'll do question 3 first, then question 4, and then question 5 in particular. Go back up the whiteboard here. Alright, so question 3 basically was for us to simplify this following block diagram here, and then hence obtain the closed loop transfer function. So I'm going to draw that block diagram on the whiteboard before we start, and then I'll show you guys like what steps we're going to be taking in particular to actually attempt to resolve this in particular. So that way you guys actually can see each one of the steps when we start resolving this. Pull up this whiteboard here. Start drawing this in particular. You guys actually see how we're doing this. R issue. One. Two. Okay. E. Here. Yeah. Alright, nice. So that actually should be our block diagram. Yeah, that's our block diagram in particular. So our first step would be to move this particular takeoff point here to the right of G4. So drag this right. So I'll move this takeoff point to the right of G4. So I'll be going this way here, drop in that takeoff point here. So this will actually be our first step. And then our second step will be to move this summation junction here to the left of G1. And I'll be putting that summation junction here on the outside. So I'll be moving this part here. we're going to be putting that outside. Now, a question some guys are going to ask in particular, or anybody wants to ask in particular, is okay, why didn't you put the summation junction here before? Or why you put it on the outside here? It doesn't really look like it makes much sense. Now, the reason with this being is that when you have a series of summation junctions going next to each other, so like, throw this in green for you guys. Let's say if you have, in this particular case, you have signal coming in here, this, and then you have another summation junction here, say like this. You can reorder those summation junctions in any order that you wish. It's basically going to give you the same end results as such. So in doing that, this is actually similar to saying, okay, let's start with this summation junction first, and then let's go ahead with the other summation junction afterwards. It's basically the same thing. So you can reorder summation junctions once they are sequential in nature, being that they're connected in a straight line. You can reorder them as such. As long as there's no takeoff points or in between them, you can do this accordingly to manipulate your block diagrams in particular. So that actually helps us with moving the summation junctions for what we require. Right. So in moving our first takeoff point here from the left of G4 to the right of G4, that means that this affected block here, we're going to have a 1 on G4 component occur. So if we erase this and then put that takeoff point where it's required, that means we're going to have 1 on G4 here. And then this being step 2. If we move this summation junction here from the right of G1 to the left of G1, we're also going to have to compensate for this as such. And the rules for these were done in the block diagram simplification lecture for when you're moving a takeoff point from to the left to the right of a block, and when you're moving the summation junction from the right to the left of a block. So in moving this, that means the compensation here on this line, this dashed red line, means it's going to be 1 divided by G1. So raise this here because it's no longer going to be here. Just here on this rate. Factor this in now. That means that we're going to have a 1 divided by G1 here. Here. And our new summation junction coming in here. Let's put the space right, nice. Go here, R, there, nice. So in one swift move, we basically moved our takeoff point and our summation junctions to the outside or the extreme edges of the block diagram. And basically, we just make sure that we compensated as such for when we moved it accordingly to obtain our compensation blocks in particular. Now, because we did this, and we moved very strategically in doing this, that means that this part here is now a negative feedback system. Dash this off here, give you an idea. So that's a negative feedback system. And this here, also a negative feedback system. So it's possible for us to reduce those two negative feedback systems using our standard negative feedback equation, which was basically, for this particular case, it'll be G on 1 plus H, where G would have been representing our feed forward block here, and H will represent our feedback block here in particular. So let me undo that because I'm going to reduce these in particular. Right. So let's do the mathematics for reducing yes. So let's do the mathematics here and reducing our first negative feedback system here accordingly. So our G block here is going to be G1, G2, and our H block here is going to be H1. So we basically know this is going to be G over 1 plus H. This comes as G1, G2 divided by 1 plus G1, 1. So this entire system here reduces to one simple block, and we get rid of that summation junction in particular. Remember, the general strategy for when you're reducing block diagrams is to get rid of the summation junctions as quickly as possible, as strategically as possible. That entire thing just resolves to G1, G2 divided by 1 plus G1, G H1. Similarly, because this is also a negative feedback system, that means we can also apply our negative feedback system equation to reduce this and get rid of this summation junction here as well. So the G here is going to be G3, G4, and our H here is going to be H2. So if we apply this to our standard equation, we basically see that's going to be G3, G4 over 1 plus G3 for H2. So this here reduces to that one simple block as of such. G3, G. Because we have these parts here being in sequential order, we're going to just multiply these blocks here accordingly. So we get H3 multiplied by 1 on G1 multiplied by 1 on G4. So this will just go to H3 divided by 1, 4. Putting as a placeholder here for now. So I'm reducing this. This is going to be H3 divided by G1. And because we have this now, this comes like if we have our positive feedback system. So for the positive feedback system, we basically know that the equation for a positive feedback system here is going to be G all over 1 minus h positive feedback. Where the G here represents the blocks on the feed forward path here, and the H represents the block here on the feed back path here in particular. So I'm doing the mathematics for this. We erase this because I'm going to need some space. That means our G here is going to be G1, G2, G3, G4, all over 1 plus G1, 1 plus G3, G4, H2. And our H block here is going to be H3 divided by G1, G4. So this basically is going to be our final step here, because this is going to represent the transfer function in between R and C accordingly. So this is going to be G divided by 1 minus GH. So it's going to be the output here, it's C divided by the input, is equal to G divided by 1 minus H. So this comes like we say 1, G2, G3, G4 divided by plus G1, G2, H1, 1 plus G3, 4, 2, all divided by 1 plus minus bracket this G1, G2, G3, 4, G2, 1 plus G3, G4, 2 into H. Oops, that's too much. Into H3, 1 plus. And then we can actually all do our mathematics accordingly for this as of such. So we can multiply out the entire thing by 1 plus G1, G2, H1 multiplied by 1 plus G3, G4, H2 multiplied by G1, G4 on the numerator and the denominator. So, and doing so, that's right. We get C on R here is going to be, make sure I'm writing this correct. Alright, okay, yeah, okay. So, because we have maths here, it's going to be like this G1 here will cancel with this G1, and this G4 here will cancel with this G4. So we just need to multiply out accordingly by 1 plus G1, G2, H1 multiplied by 1 plus g3, g4, h2. So that means that our numerator here will become g1, g2, g3, g4, all divided by 1 plus g1, g2, h1, 3, 4, 2, minus g2, g3, g2, g3, 3. And how we did that was that we basically multiplied the numerator and denominator by 1 plus g1, g2, h1 multiplied by 1 plus g3, g4, h2. So, oops. Right, stay there. So, that basically gives us our representation of what our final transfer function should be. And if we plan that out even more, we do some more math, we can get into even a more expanded form, or we can just keep it in a simplified form here, which is perfectly acceptable as of such. That's perfectly fine as well. So that actually is how we attempt to solve question 3 in a more strategic manner. The solutions that I'm going to post up will show you guys this strategic manner as well as another approach that is slightly longer and takes a little more steps. But like I said, when you're actually reducing the block diagram, there isn't one unified approach in reducing it. There are multiple ways to reduce it. All approaches are fine. Just that there will be some approaches that may be shorter than others, but it's perfectly fine. If you take a longer approach, you wouldn't be penalized as of such. So are there any particular questions for question 3? The 1 in the denominator here gets multiplied out only by this denominator, by this factor here. So it comes like, we say, for this factor here, sorry, let me change the ink. It comes like we say, for this denominator factor here, we multiply that by the numerator and denominator. So because this factor here is going to be multiplied on the numerator, this here is the same as the denominator here at this point. So those two just cancel. But when we multiply it on the denominator here for the entire fraction, this comes like the 1 here multiplies by 1 plus g1, g2, h1 by 1 plus g3, g4, h2. So that's where the 1 here gets replaced by that multiplicative factor. And then, because this is g2, g3, h3, when we multiply by this red underlined factor here, this just cancels with it. So that's how we end up with minus g2, g3, h3 here, representing just this part for this particular aspect. So that what happens to that one factor here, because we multiply this by, we multiply the numerator and denominator by this combined factor here. And any further questions? Basically, once you get a nice representation like here, it's perfectly fine for the simplification. You just don't want to have any square or cube components here for G1, G2, G3, G4. Any of the G or H components, make sure it's not squared or cubed. It just needs to be to the power of 1 as of such. So this is an okay representation. There may be some cases where the question may explicitly ask you to expand out the answer such that you don't have it in a factorized form. So that in those particular cases, you're going to have to multiply out everything accordingly and write it straight out. But if it doesn't ask for that in particular, this factored form here is pretty much okay. What you cannot have is fractions on the numerator and fractions on the denominator. That is not acceptable as the final answer. So you need to make sure that the numerator and denominator here, basically, they don't have any fractions. They are represented as their individual parts as of such. So I guess the better terminology for this is that the final answer needs to be a proper fraction. It can't be an improper fraction, like where you have a fraction here on the numerator and then you have a fraction here on the denominator. So it needs to be a proper fraction altogether. Alright, doesn't seem like we have any more particular questions on question 3. So in that particular case, let's move on to question 4. So question 4 here basically asks to determine the closed loop transfer function for the system. So let's actually observe the system here, and we basically see that it's our standard negative feedback system where our G block is going to be represented by this block here, and our H block is represented by this block here. So let's go back to our whiteboard in particular. Whiteboard. Yes. So this is our standard negative feedback system here, as we observed in our question. So the transfer function here being y of s on x of s is going to be y of s divided by x of s, going to be g divided by 1 plus h. And g here represents our feed forward block, which is going to be s plus 1 divided by s squared plus s plus 1. S plus 1 divided by s squared plus s plus h here represents our feedback block, was a divided by s plus 2. That's correct. Right. So let's plug this into our transfer function. So this comes such that it is s plus 1 all over s squared plus s plus 1, all divided by 1 plus, open our brackets here, s plus 1 squared plus s plus 1 into t s plus 2. And we can see here that the denominator factor here for the overall denominator is going to be a combination of these two factors here. So we're going to have to multiply our numerator and denominator accordingly by that combined factor here being s plus 2 into s squared plus s plus 1. So, like I said, we're multiplying, So we want to be multiplying our numerator and denominator by that combined factor. So y of s divided by x of s is going to be, so when we multiply our numerator here by this combined factor, the s squared plus s plus 1 here will just cancel, but we'll have s plus 1 multiplied by s plus 2 on the numerator. So this is going to be s plus 1, s plus 2, all divided by, we have this one factor here, so that's 1 multiplied by this factor that's combined here, so that's just a representation of it, s plus 2 into s squared plus s plus 1 plus, and then when we multiply this combined factor here by the multiplication of these two, the denominator here and this factor here will just cancel, so you just get k multiplied by s plus 1, k into s plus 1. Back one. Yep, that's correct. So, just for argument's sake, let's multiply this out. So this plus s squared plus 3s2 into s cubed plus s squared plus s 2s squared 2 plus as k s squared 3s2 into s cubed plus s squared components will be 3s squared plus s into, so the s's here will be 3s plus ks, this is 3 plus k plus 2k. Which will basically give us our final answer equality for our transfer function. So, is there any particular questions? Sorry, are there any particular questions for question 4? So for this particular problem, yes, the square and cube does not matter here because it's S and it's not G or H. Because remember, we're dealing with this with respect to the S domain. So yes, you can have S cubed, you can have S squared, you can have S to the power 4. Yeah, so it doesn't matter here in this particular case. But when you're dealing with components being, when we have G and H, remember that's G of S and H of S. And you can't really have a G squared S or H squared S because that comes like you're basically multiplying the system by itself again. So when you're dealing with it with respect to S, you can have any power factor associated. But if you're dealing with respect to G and H and whatnot, you can't have any power factors for those. Those have to be at the power of 1. Any further questions on question 4? Typically, like the block reduction question that was on uh, your so your midterm is basically depending on how it's weighted. Let's go on percentages. So your midterm is about 20%. If you get a question that the block reduction, it will be 8% of that 20%. If you get one of these standard negative feedbacks, which is like a little bit simpler, it will be weighted way less. But like things like block reduction and so forth, it would be like 8% over that 20% question in particular. If it comes on the final exam, it will be a block reduction question will be like 10 marks out of the 100 marks in the final exam. Alright, so move on to question 5 in particular. And that was the last question to do with respect to problem set 3. So this question basically was asking what's going to be the output response of the system to a sudden input change of 5 degrees on the control knob if you're given values for K, Km, and Kp. So before we actually get to that particular question, that means we need to obtain the transfer function that maps theta out and theta in particular. And this also is a standard negative feedback system. So back to our whiteboard. Stylus here. So because this is a standard negative feedback system, this also follows our standard negative feedback equation, which is going to be G divided by 1 plus G of H. Instead of this being Y and X here, this now becomes theta out of S, theta in of S. So the G block here would be the combination of the blocks here on the feed forward part, which would be Km divided by S multiplied by K divided by S plus 4. So Km divided by S multiplied by K divided by S plus 4. Km S 4, and our H block would be our feedback only, is going to be Kp. So, and resolving the transfer function out S in, let's substitute it in G and H accordingly into our equation. So this will become A divided by S plus 4, all divided by 1 plus A and A divided by S plus 4, multiplied here by Kp. And rectifying this into a proper fraction, basically see that this here is just the only component that we would have to multiply the numerator and the denominator by. So as of such, this here will resolve to, if we multiply the numerator by that factor here, these two factors here will cancel because they're basically the same. So the numerator becomes Km this in consistency, and our denominator now becomes, well, because we have 1 here, 1 needs to multiply by this factor, so we'll get S into S plus 4 plus, and because there's only this factor here for this multiplication part here, when we multiply the denominator here by that factor, it will just cancel. So you get Km Kp, which will give us our overall transfer function. Now, the question basically gives us the values for K, Km, and Kp. So that's going to be K is 2, Km is 1, Kp is 0.5. So let's write that in. K is, just make sure, 2, 1, and 0.5. K is 2, Km is 1, Kp so if we substitute that in our equation, theta out of S divided by theta in of S. So Km here is 1, K is 2, so our numerator here will factor out to 2. And we have squared plus 4S plus the 2 by 1 by 0.5, which will just basically give us 1. And the other thing we need to factor in at this point is they said the output response of the system to a sudden input change of 5 degrees for this particular case. And we just now substitute in our values here for K, Km, and Kp accordingly to get our reduced transfer function eliminating all these k components in particular. So the only other thing that we didn't factor in was this input change of 5 degrees. So because it's an input change of 5 degrees, this is similar to that it's going to be a step change as of such. So because it's a step change, so there's going to be a 5-degree step input in t. We know that when we watch our Laplace transform table, our step change for a value of 1 is going to be 1 on s. So if it's 5 degree, if it's a 5-degree step input, meaning that the magnitude is going to be 5, that means when we transfer that 5 value in time to the s domain, it's going to be 5 divided by s. So means we'll have theta out s is equal, and before we substitute in our theta in of s, 2 theta in of s divided by s squared or s plus 1, and now we're going to actually substitute in our theta in of s. So this now becomes 10 of s squared plus 4s plus 1. And we rectify this into a proper fraction. This here is going to be 10s into s squared plus 4s plus 1. So in the interest of time, let's actually use our partial fraction calculator. To actually resolve this for us. Sorry. So make this into a fraction. So this is going to be 10 s into s squared plus 4s plus 1. Cool. Let's see all the steps here. So in doing the steps, we basically see that the partial fraction separates out the s and the quadratic components here. And we basically see that when we start resolving this, for our components, this being a0 is 2s and a1 here, we see that we got 10 on s plus minus 10s minus 40 divided by s squared plus 4s plus 1. So let's actually write this in. So theta out of s 10 of s minus, I'll say well plus here, just to say for simplicity, minus 10s 40 correct into squared plus 4s. Let me just check back the question here. Alright, we need this answer in terms of time. Okay, nice. Alright, so this factor here, we realize that if we try to factorize this denominator, we're going to get imaginary roots. In doing so, we don't really want imaginary roots when we're trying to solve for our Laplace transform. So we're going to have to complete the square here on the denominator in order to proceed. So I'm going to be focusing on only this part of the equation for the time being. So we have minus 10s minus 40 divided by s squared plus 4s plus 1, and what is it, minus 10s minus 40 into s squared plus 2s plus 4 and plus 1 minus 4. If I complete the square there correctly, that's s plus 2 all squared, so no, I did not complete the square there correctly. Hold on, let's make sure I do it correct. Inverse Laplace transform calculator, that's what I'm looking for. Simple. So let's factor this in our works equation. So we'll start back with this equation here using the inverse Laplace transform calculator, which actually shows all the steps as to what we're looking for when we're completing the square. So that's going to be 10 divided by s minus 10 divided by s squared plus 1. Go here. Make sure. Oh, okay, nice. Yeah, I did correct. Okay. So, in doing this, when we actually focus on that point here, you see that this basically resolves to 10s 40 into s plus, oh, whoops, right, doesn't have to be 2s, 4s. S plus 2 all squared. Just 1 and minus 4 will give us minus 3. And in doing so, let's bring up the Laplace transform table quickly so that I can show you guys what's the associated transforms. We see here that the associated transform for this, it's going to be the E of AT transform sine of BT and the E of AT transform cosine of BT here. So we're going to have a B factor here and an S minus A factor to get the associated time transform. So this B factor here needs to be associated with B squared, and this A factor here is going to be associated with the A that's in the bracket here for our square term. And the inverse Laplace transform calculator basically gives us the steps on how to do this in particular. So because it's in that form here for 10s minus 40 as such, it also resolves the numerators for you accordingly in order to get to your answer. Oh, these guys give you the respective cosine h and sine of h. Okay. Actually, alright, so I'm gonna actually have to do the work in here in this particular case. Alright, so in this particular case, we want to get to the terms of e to the at sine of bt and e to the at cosine of bt. So that means we're going to have to get b squared here on the denominator. In this particular case was go back here. B squared here. Oh, okay, no. It has to resolve into sine h because it's minus b squared. Right, okay, yeah, okay. So in this particular case, we'll be focusing on using the e to the at sine of h bt and the e to the at cos of h bt. And the reason for this being is that we have minus b squared here instead of positive b squared. So once you see minus b squared here, meaning that this factor here is minus, this is going to resolve into e to the at sine h of the factor, and e to the at cos h of that factor in particular, because of this minus 3 here. So right, the inverse Laplace transform calculator has it correct. So the steps here are given to you guys for actually how they actually do this in order to resolve it. So you basically see that they figure out how to factorize it such that they get s plus 2 on the numerator here to get that associated Laplace transform for e to the at sine of so e to the at cosine h of bt to get this s minus a factor, or in this case it will be s plus a factor. And then they make sure that they get this b here associated to get to the transform of e to the at sine h of bt. So that basically shows us how we actually get this accordingly in order to get to our actual transforms. And all the workings here are shown actually how you obtain this accordingly to get to these questions, these factors in particular. So the end result is, at that point you'll get your final answer being, well, they say the result is with respect to ht, but this is going to be, then ht here is basically u of t. So so this is going to be delta out of t. At that point it's going to be 10 u of t. This here accordingly, minus 10 e to the minus 2t. This is cos h factor, cos h of root 3t minus, because it's minus 20 divided by root 3 e to the t sine h 3 of t. So the inverse Laplace calculator here is actually quite handy to show you guys actually how it does resolve these factors here for you guys, and it shows you guys all the working required to actually obtain these factors in particular. So make a lot of use of this, especially for when you're actually doing your problems in particular, because this will actually help you quite a bit when solving your Laplace transform equations. Alright, so are there any particular questions for question 5? Alright, it doesn't seem like we have any questions for question 5, so that brings us to the end of the selected problems for problem set 3. and I will post up the solutions currently for problem set 3 online, so you guys can see the solutions for the questions 1 and 2 in particular. So at this point in time, let's take a short 5-minute break, and when I come back, I will start doing the midterm review stuff, because I'm going to have to do a little bit of prepping on the computer to organize the particular questions that we want to be doing. So give me 5 minutes and come back in 5 minutes time, and I'll start doing the midterm review session in particular. Alright, hopefully everyone's back at this point in time, because I've a little bit more than 5 minutes at this juncture. So, at the start of our review session, we're going to be focusing on, next. We're going to be focusing on a particular problem that was shown in your lectures for your homework. In particular, this would have been this block diagram here for lecture 14, which was given to you guys for homework. So I'm actually going to go through this in particular and the strategy that we're going to be using to reduce this block diagram. So I just drew it out here on the whiteboard for you guys, and we're going to be actually reducing this as we're going along. So the general strategy in reducing the block diagrams is that we want to make sure that we get a whole set of negative feedback systems or positive feedback systems as such, so that we can start eliminating all of these summation junctions in particular. So we're going to get rid of this summation junction, this one, and this one. What order we get rid of them doesn't really matter, so long as we do get rid of them. And the only way to get rid of them is to have feedback systems accordingly to reduce. And in that process, we get rid of blocks in particular, as well as the summation junctions as of such. So the strategy I'm going to use here is that we're going to be trying to move this takeoff point here from the left of G3 to the right of G3, and in doing so, the takeoff point will give us this negative feedback system here accordingly, just to reduce. So let's actually go back to our rules here in particular. We're moving the takeoff point from left to right. So in moving this takeoff point here from the left of G3 to the right of G3, so let's move this. I'm going to put this on the outside here. The compensation is that in moving to the left of a block to the right of a block, we're going to have to divide by that affected block, so that's going to be 1 divided by 3 here. And because we did this move here, that means now we're able to actually reduce this negative feedback system here, where we have the forward part here being represented as G, being G2 and G3, and our feedback path here being H2. So let's say I'm going to write this down here for reference. G is equal to G2, 3. H here is going to be equal to H2. And we know that basically it's going to be G divided by 1 plus H for a negative feedback system. There's going to be G2, G3 divided by 1 plus G2, G3, H3. So, in reducing this, we get rid of this summation junction, get rid of the G2 and G3 blocks here, and get rid of this H2 block here only. So, this just reduces down one block here being G2, into 1 plus G2, G3, H3. Let's erase this because we no longer need this at this point. Hurry this up a little bit. Our next step here is that we basically see H1 and G multiplied by 1 and G3 here, so let's just combine these two blocks one time. This will become H1 divided by G3. So the next step here is that we have a positive feedback system where our G blocks here for the feed power path is going to be G1 and this G2, G3, 1 plus G2, G3, H3. And our feedback being our H block is going to be H1 and G3. So for our positive feedback system, we know that the transfer function is going to be G divided by 1 minus GH. So basically this is going to be G1, G2, 3 divided by 1 plus G2, G3, H3, all divided by 1 plus, bracket this off, G1, G2, 3, 1 plus G2, G3, H3. Use this in the meter. Multiplied by H1 divided by G3. And immediately we see here on the denominator, this G3 here will just cancel with this one. And our common factor here will just be this here to multiply by the numerator of the fraction and the denominator of the fraction. So this entire thing will just resolve to G1, G2, G3 all divided by 1 plus G2, G3, H3 plus G1, G2, H1. Oh, sorry. We no longer have G3 here. It's going to be G1, G2, H1. Oh, no, sorry. Whoops. I'm doing that wrong. Right. No, that's correct. G1, G2, G3. Yeah. But we multiply by this denominator. Right, that's cool. And then there's 1 here, we multiply by that. So we get 1 plus G2, G3, H3 plus G1, G2, H1. Alright, yeah. This is the correct phrase. Yeah, 1 minus. Sorry. Yeah, thanks for pointing that out. 1 minus. Yeah, we'll end up being minus. There's still plus. That's plus. There. Minus. Yeah, thanks for pointing that out. Yeah, because 1 minus GH. So this 1 here will multiply by that factor here, so it'll be 1 plus G2, G3, H3 minus this factor here will cancel, so it'll be minus G1, G2, H1. That's so that means we get rid of this summation junction here, the G1 block, this block here, and this H1, G3 block here in particular. So we can erase those. Put in one huge block here. Representing our new summarized version, which is G1, G2, G3. And divided by 1 plus G2, G3, H3. Minus G1, G2, H1. So let's erase this work in here. Okay, so it's recorded, so you guys can actually watch this back and see the actual work in. All of this working for the time being. Okay. So at this point, when we reach here, we see this is negative feedback. So the standard transfer function would follow such as it's g over 1 plus gh. Now, the feed-forward path, we know this is here is going to be our g block. But the feedback path there, we just see it's going to be just a line. And when you have a path there which is just a line and there's no block, that means here that the block value that is associated with this line is just going to be 1. So in this particular case, h here is just going to be equal to 1. So when we substitute this into a negative feedback equation, so this is going to be C divided by R is equal to that, because it's output divided by input. Put this in, so G here is going to be G1, G2, 3 divided by plus 2, G, 3, G1, 1, all divided by 1 plus G1, G2, G3, 1 plus G2, 3, G1, G2, 1 multiplied by the value of 1 for h. Our common denominator here is this factor. So if we multiply that out accordingly by the numerator and denominator, C divided by R here is equal to G1, G2, G3, because this factor here cancels with this factor here, they're basically the same. The 1 here will be multiplying by this factor here, so we'll get 1 plus 2, 3, h3 minus g1, g2, h1, and then because we multiply by this factor, it just cancels, so we get plus g1, g2, g3. Basically gives us our final answer for the transfer function. So as we saw in doing this block diagram simplification, let's go back to the homework problem that was given to you guys in lecture 14. The idea was basically to get rid of each one of these summation junctions, and the only way to get rid of each one of these summation junctions here is to incorporate feedback systems and reduce the feedback systems to get rid of those and the associated blocks. So strategically, we basically see that there's a feedback system here, but there's a takeoff point that requires to be moved. So we move this takeoff point here to the right hand side, and then we reduce this accordingly and got that associated block. And then when we had that associated block, we see that this here would have just been another feedback system, so we reduced that. And then we had this final summation junction to reduce for that feedback function. When we reached that point in particular, we saw that yes, we had our feed forward block here being our G block, but the feedback line here basically did not have a block. And for any line that doesn't have a block, the block value basically is going to be 1. So the G block here, being our feed forward block here, was represented by this block here, but our H block here being our feedback block. Because there's no block here, that means H here is just going to be equal to 1 associated. We just plug this into our standard negative feedback equation, and we reduce the fractions accordingly, and we get our final transfer function mapping C our output to R our input as a sum. So yeah, it's basically for you to observe the general strategy when doing block reduction, just to apply it accordingly, so that way you can keep on reducing the block diagram to get rid of each one of those summation junctions. That's just a general strategy to apply when you're doing block reduction in particular. Are there any particular questions associated with the strategy of the block reduction question? So when the denominator is 1 plus g of h, that's a negative feedback system. And when the denominator is 1 minus g of h, that's going to be a positive feedback system. So you can watch straight from the diagram here, is that you see that the feedback line going from the output to the input here, sign at the summation junction is negative. So this is going to be a negative feedback system. So negative feedback systems, the denominator is going to be 1 plus g of h. If this sign here was positive, on the other hand, then it's going to be 1 minus g of h equally on the denominator. Alright, it doesn't seem like we have any further questions regarding the block reduction strategy. So let's move on to the other sort of question that you may be expecting to come in your midterm in particular. And drop the whiteboard here in this particular piece. Better canvas. I think I'm going to need to grab this problem here for you guys. Alright, so let's say we're given the following differential equation here. It would be y double prime minus 10y prime plus 9y is to 5t. Given initial conditions here where y of 0 is equal to minus 1 and y prime of 0 is equal to 2. We need to solve this accordingly. So in solving for this, let's say we want to be using the Laplace transform. Taking Laplace transform of both sides. So y double prime here, the primes basically represent the order of differential. So if you see a double prime, that's a second order differential. If you see a single prime, that's a first order differential. If there's no prime, it's just y or x associated with the equations in particular. So because this is a second order differential for y double prime, this is going to be s squared y of s minus s y naught minus y prime naught, and then we have minus 10y prime here, so there's going to be minus 10 into s y of s minus y naught, and we have plus 9y, so this is going to translate to 9y of s equals, so we have 5t here, and we have 5t, and we need to figure out, okay, this being 5t, what's going to be our associated Laplace transform with this. So we're going to go to our Laplace transform table here, and we basically see that for anything that's t of n, it's going to be n factorial divided by s to the power n plus 1, and as of such, that means that because this is t to the power 1 factorial here is going to be 1, but this is going to be s to the power 1 plus 1, so that's going to be s squared, and the 5 is basically a constant. So that means 5t will translate to 5 divided by s squared. We could substitute in y naught and y prime naught here. So we'll basically get s squared y of s minus y naught was -1, so -1 minus s now becomes positive s. Y prime naught was 2, so this will become 2 minus 10 s y of s plus, because this here is going to be minus 10 by minus y of naught, so that's going to be a positive here. That's also going to be a negative here, so that's 3 negatives that have been multiplied, so this is now going to become minus 10 multiplied by minus 1, so that's become 10 minus 10 by 1, so let's go here, it's going to be minus 10. Plus 9y of s is being equal to 5 on s squared. Right. So let's factorize out all y of s here into s squared minus 10s plus s component here, yes, minus 2 minus 10 will give us minus 12 equals 5 s squared. Alright, s here, s squared, s equal to 5 divided by s squared minus s plus 12, and we can do some manipulation here to get y of s to be the subject of the formula. So in this, get 5 into s squared into before I move on here, factorize the left hand side. So this s squared minus 10s plus 9 here can become s minus 9, s minus 1. So s minus 9 minus 1. So y of s in this case can become 5 on s squared s minus 9 S1 plus 12 minus S into S minus 9 S minus 1. And then we can combine the two together. So y on S here will become 5 plus 12s cubed. Oh, sorry, 5 plus 12s squared s cubed, all divided into s squared into s minus 9 . The partial fraction equivalent for this, because we're going to have to do partial fractions and then do the inverse Laplace transform, y of s here is similar to a divided by s plus b divided by s squared plus c divided by s minus 9 plus d in s minus 1. If we equate the numerators accordingly for partial fractions equivalents, that means, so written numerators, means we get 5 plus 5 plus s squared cubed is going to be equal to a s into s minus 9 1 plus b into s minus 9 s minus 1 plus c into s squared s minus 1 plus d s squared 9. And then let's say in this particular case that's s equals 0. So what we end up guessing is 5 is equal to 3. So b is equal to 5 over 9. S equal to 1. Get 16 is equal to minus 8d. And that d here will be equal to 2. S is equal to 9. Get 248 is equal to 648c. That c here is equal to 31 divided by 81. And then when s here is equal to 2, solve for our last factor, we get 45 equal to minus 14a plus 4345 by 81. Means a here, when you resolve that, it's going to be 50 divided by 81. So when we plug in all these factors here for y of s, this is going to be 50 on 81 divided by s plus 5/9 s squared plus 31 on 81 divided by s minus 9 minus 2 into s minus 1. And then when we take the inverse Laplace transform, when we get y of t here, so because this is divided by s, the inverse Laplace transform, this will just be 50 divided by 81. This one here, because it's divided by s squared, means that we'll be having a t factor here. So this will become 5 divided by 9 multiplied by t. S minus 9 means that this is going to be an exponent factor. So this will become 31 divided by 81 of e to 90. And s minus 1 here also means this is also going to be an exponent factor. It's going to be minus 2 e to the t, which gives us our answer for y of t accordingly. Right. So are there any particular questions as to how we attempted the solution here for our differential equation? Alright, doesn't seem like we have any further questions at this point in time. So you can expect these kinds of problems to typically come on the midterm in particular. And my advice to you at this point is just keep on practicing with respect to these as such. I did mention there were three questions that will come on the midterm. And you have an idea of the topics here from this review session. But there will also be an unknown topic that I didn't cover here that will be within the material of the first 14 lectures that will also come as a question. But these questions that I gave you, this will be like the majority of the marks on the midterm that will be covered with respect to these kinds of questions. So my advice to you is to practice these particular types of questions that we just did here in this review session. That way you're pretty much prepared for what's coming on the midterm as of such. And if you guys have any further questions, please feel free to leave them down in the comments below, or you can email me directly and I'll get back to you accordingly within a reasonable time frame. Just remember that the midterm is going to be next week Tuesday, and as of such there won't be any class on Monday for preparation of the midterm on that Tuesday in particular. So remember, no class on Monday, guys. Next week is just going to be strictly your midterm week for this course. So, like I said, if you guys have any questions, email me it anytime before the midterm. Try not to do this last minute. Try to get in your questions earlier as of such. And I'll answer you guys accordingly once I'm anywhere nearby the computer in particular. So, good luck on your midterm next week. And until then, take care, be safe. I will see you guys soon. Later. The midterm is, for our particular case, it's going to be 12 hours from 8 AM to 8 PM. The details for the midterms are on the My Learning forum. So you can get all the details there on the forum post.